Hello guys, welcome back to my channel. And today we'll be doing an integral that's all about Leibniz rule, otherwise also known as Feynman's integration technique. So if you don't know this technique yet, this is a good video to learn that from scratch. So as always, let's get to it. So as always, we have our problem. Let's call it I. That is the integral from 0 to pi over 2 of the inverse tangent of sine of x all divided by x sine x integrated with respect to x, of course. Now looking at the structure of the integrand, you might be tempted to somehow use a Taylor series, but I'm telling you right now that doesn't end up in a good place. And since, as I declared at the start of the video, that we're going to be doing the Leibniz rule or Feynman's integration technique, so I won't disappoint you, because if I don't know, you guys might just leave the video if I try make any attempts with other integration techniques, if you wanted to learn Leibniz rule from scratch. So let's use Leibniz rule. uh, Leibniz rule of basically differentiating under the integral sign. And why do we say differentiating under the integral sign? Because to apply Leibniz rule, we first need to define a general case of our problem integral. So I'll just show you in a bit. So how do we generalize our problem? So we have our I. Let's make it a function of b. So it's sort of parameterizing it. It's sort of parameterizing our problem, because we introduced um, this parameter of b that was not known before. So we still have the integral from 0 to pi over 2, and then we have the inverse tangent of b multiplied with the sine of x inside the argument, all divided by the sine of x dx. Now I introduced the parameter inside the argument because when I differentiate under the integral sign using Leibniz rule, then I am going to get rid of the sine of x in the denominator, because it's going to get cut with when we apply the chain rule in the numerator. And in case you're clueless at this point of time as to what I'm saying, don't worry. Let's go through this process together. So I'm going to use another page, and I'll ensure that you guys learn a lot today. So as I said, we have a generalized problem, say I of b, which is defined as the integral from 0 to pi over 2 of the inverse tangent of b times sine of x divided by sine of x integrated with respect to x, of course. Now we first need to differentiate both sides with respect to b. So I'm going to do that on both sides here of the integral, the derivative with respect to b of the integral from 0 to pi over 2 of the inverse tangent of b times sine of x divided by sine of x dx. So I can represent the derivative of I of b with respect to b as I prime of b. This is basically a Newtonian notation, and it's a common practice to denote the derivatives of functions throughout. You might know this notation throughout your calculus course, or in textbooks and stuff like that. So fine, I want to now take the derivative inside this integral. Well, that's what the Leibniz rule originally dictates, right? It's the Leibniz rule is not exactly an integration method like U substitution or something, but um, Leibniz rule basically says that if you were to differentiate an integral, you can take the derivative inside the integral sign, but then it gets converted into what's called partial derivative. So a partial over partial b of the inverse tangent of b times sine of x all over sine of x. So the partial derivative is acting on the entire integrand like this, and we still have our dx. Now in in other cases where say our upper and lower bounds were functions of b somehow, functions of our basis of differentiation somehow, we would have to add certain other values, but since pi over 2 and 0 are constants, all those other values that we are supposed to add basically become 0. I'll explore the Leibniz rule in more detail in another video, but for now it works like this. So a partial derivative with respect to b, we use this partial derivative sign because inside the integral we have functions of x and we have functions of b, right? So we need to quite distinguish we're taking a derivative with respect to what. So now all the x terms are basically constants in the b world, right? So we can just take them out of the derivative operator. Sorry, pi over 2, not pi over 4. So we have our integral from 0 to pi over 2 of 1 over sine x, because x is a constant with in the b world, and then the partial derivative of the inverse tangent of b times the sine of x. Now we can't just um, ignore the inverse tangent and just pull it out of the differential operator, because it has a b term in the argument, so we'll have to apply the chain rule. The chain rule of regular integration. So we have the integral from 0 to pi over 2 of 1 over sine of x. Then when I apply the chain rule, I have the derivative of the inverse tangent is 1 over 1 plus the argument squared. And what's the argument? B times sine of x, the whole thing squared, and times the derivative, so partial over partial b of b times sine of x, right? That's the chain rule. Don't forget your dx, because everything is still under the integral sign. So we have the integral from 0 to pi over 2, 1 over sine of x times 1 over 1 plus b times sine of x, the whole thing squared. And then since sine of x is a constant in the b world, you can just pull it out, and the derivative of b with respect to b is 1. So you don't, you can just multiply 1. Just ignore that because it's a product. So look what I was saying at the start of the video. I said let's introduce the parameter b inside the argument of the inverse tangent. Inside the argument of the inverse tangent, like this, because then when we differentiated under the integral sign, we would cancel the signs out like this. So in one way we got rid of our denominator. So the Leibniz rule of differentiating under the integral sign is very useful when we want to really get rid of our crazy our crazy maddening denominator. Say when it was only, even if we only had a single x, or a complex function like the sine of x, cosine of x, stuff like that. So we have the integral from 0 to pi over 2 of dx over 1 plus b times sine x, the whole thing square. Now we really need to simplify our I prime of b. Let me remind you what all this was. It was I prime of b, right? I prime of b all along. Yes, so we can actually simplify everything further by actually calculating this integral. And the funny part is, to find a derivative of I of b, we need to integrate. So that's sort of an irony here, but that's how calculus, advanced calculus works. So let's go ahead and calculate this integral. So we have I prime of b being equal to integral from 0 to pi over 2 of dx over, let's just square everything. We have b squared times sine squared x dx, and I want to divide everything, the numerator and denominator, obviously, by the cosine of x, cosine squared of x rather, because we have a sine squared, and you will see in a minute why. So we have integral from 0 to pi over 2 of 1 over cosine squared x is secant squared x. There was no need for a dx, I'm so sorry. Dx over 1 plus 1 over cosine squared x here. So 1 over cosine squared x plus sine squared x divided by cosine squared x is b squared as it is, tan squared x, and we have the dx. So we can just simplify the denominator a little bit. So we have secant squared x over 1 over cosine squared x is secant squared x again, plus b squared tangent squared x dx. Now we know that the secant squared x can be written as 1 plus the tangent squared x. So I want to go ahead and do that. So we have the integral from 0 to pi over 2 of secant squared x divided by 1 plus tan squared x plus b times tan squared x integrated with respect to x. Now I want to just group some terms here. So we have the integral from 0 to pi over 2 of secant squared x over, why don't we group the tan squared x terms together? So we have b plus 1, sorry, it's b squared. So b squared plus 1 times tan squared of x plus 1 dx. Now I want to really introduce a substitution. So I want to let u equal tan of x, because the derivative of tan secant squared x dx is on top. So as I said, du is secant squared x dx, just our numerator. So, and now we want to plug in our upper and lower bounds. So when x is 0, we can plug in 0 here. We have tan of 0, which is 0, so u is 0. When x is pi over 2, we have tan of pi over 2, which is infinity, so u is infinity. So this is basically our substitution all over here. So I prime of b is nothing but integral from 0 to infinity of du over b squared plus 1 times u squared plus 1. Now I really want to factorize this b squared plus 1 term outside. So we have 1 over b squared plus 1. It's a b is a constant with respect to u, so we can just pull it out of the integral in case you were wondering. The integral from 0 to infinity of du over u squared plus 1 over b squared plus 1, because there wasn't a b squared plus 1 term here. Since we factorized b squared plus 1, we need to maintain equality by dividing 1 with b squared plus 1. So now I'm going to rewrite this thing as well. This is unchanged. We have the integral from 0 to infinity of du over u squared plus 1 over b squared plus 1 square root of that, but the whole thing squared. So in one way, if you didn't catch that train of thought, the square root and the square are effectively going to cancel out, yielding us a single normal term, raised to 1 power. But the purpose of doing this is because um, we have an integration formula, if you will, to calculate integrals like this. So we have, say we had an integral of, say, dx over x squared plus a squared, and a is just a constant. We have 1 over a times the inverse tangent of x over a plus, oops, um, a constant of integration, obviously. So now instead of having the constant squared, we have dx over x squared plus just a constant. So we want to write the constant in terms of something squared. So if we have a single constant, to maintain equality we have to take the square root and then square that. So that will just yield 1 over square root of a, because whatever was inside the square is being taken outside and applied. Then we have applied this identity on that, times the inverse tangent of x over square root of a plus c. Another way of thinking about this is we just replaced our a with a square root of a. So that's why I took the square root, because we just had a simple constant like a in this, and then we want something in terms of this some constant squared, so that we can apply this great formula. So that's what exactly I've done here. So now I'm applying the formula that I stated before. So 1 over this, so 1 over square root of 1 over b squared plus 1 is basically multiplying by the square root of b squared plus 1 in the numerator, and we always have this b squared plus 1 factor outside, times the inverse tangent of, well, this is anyways going to be 1 over square root of 1 over b squared plus 1. So when we flip that up, we have square root of b squared plus 1 multiplied with a u, but since it's a definite improper integral, we have to evaluate it at 0 and at infinity. So we can actually simplify this a lot, because a single term is nothing but the square of the square root, right? So if you can imagine, one of these terms cancel out and we just end up with 1 over square root of b squared plus 1. And now since we have to deal with an improper integral, I want to do it the correct mathematical way. So let's take the limit as k goes to infinity of the inverse tangent of square root of b squared plus 1 times u evaluated from k to 0, because we can't exactly plug in an infinity. We always have to take the limit as a constant, as a variable, sorry, goes to infinity. Well, if we were to say take evaluate for the upper and lower bound, we have the square root of 1 over the square root of b squared plus 1, and then limit as k goes to infinity of inverse tangent of, instead of u we can plug in the k for the upper bound, b squared plus 1 times k minus, well, it's just a constant, so it's being multiplied with this entire thing, minus when we plug in 0 we have the inverse tangent of 0 times any constant is 0, inverse tangent of 0. Now as k goes to infinity, infinity times a small finite constant is still infinity, so the inverse tangent of infinity is going to be pi over 2. Well, the constant outside is as it is, unscathed. We have pi over 2 minus the inverse tangent of 0 is just 0, so nothing, we can just subtract 0 and nothing changes. So finally we obtained that our I prime of b is nothing but pi over 2 times 1 over square root of b squared plus 1. Well, that's I prime of b, right? Now we need to integrate to get I of b again, but it will be a definite integral, and I'll show you why. So I would like to remind you that our I of b was just the integral from 0 to pi over 2 of the inverse tangent of b times sine of x all over sine of x dx. And in our problem, if you remember, there was no b. So you can say that our original problem was a special case of this. So I, when b equals 1, is going to be integral from 0 to pi over 2 of the inverse tangent of 1 times sine of x is just sine of x divided by sine of x dx. And that's exactly our original problem. That's exactly what we need to find. And we also need one value where our I of b function is going to 0, or approaching some finite value. In most cases we tend to find a value of b where the integral becomes 0, because 0 is easiest to work with instead of some finite constant value. So now notice that when I of b, when b is 0, is just inverse tangent of 0 times sine of x is inverse tangent of 0. Inverse tangent of 0 is 0, so integral of 0 dx is just 0. Now why is this so helpful? Why did we do all of this? Is because remember we obtained an I prime of b expression, namely the pi over 2 times 1 over the square root of b squared plus 1, right? Well, I said we need to integrate that, so I'm going to integrate that, but from 0 to 1, because by the fundamental theorem of calculus we're just going to be having I of b but evaluated from 1 to 0. So basically I when b is 1 minus I when b is 0, and that's exactly what we calculated on top, right? So I when b is 1 is our original problem I, minus I when b is 0 is 0, so it's just I. So this definite integral over here is just evaluating to our original problem I. So to solve our original problem, we just need to calculate this definite integral over here. I hope I'm making sense. It's pretty logical if you think about it. So when we know that I is nothing but the definite integral from 0 to 1 of I prime of b integrated with respect to b this time, not x. So we can definitely do this. I prime of b is pi over 2 times 1 over square root of b squared plus 1 db. Pi over 2 is a constant. We have the integral from 0 to 1 of 1 over square root of b squared plus 1 db. Now I would like to go for a trigonometric substitution. You know why? Because we can use this famous identity. 1 plus tan squared theta is nothing but secant squared theta, and we see this because if we let b equal tan theta, we can actually establish this relationship in the denominator. So that's why I would like to go for trigonometric substitution. Plus, when you have these radicals and the square terms inside the radicals, it's best to use trigonometric substitution, because it's basically, I would say, the thumb rule is whenever your integrand looks like it satisfies one of these um, square identities of trigonometric functions, even say this 1 minus cosine squared theta is equal to sine squared theta, which will take the form 1 minus variable squared, even if that thing is under a root, then we go for trigonometric substitution. More about that in probably another video. So let b equal the tan of theta, tangent of theta, so that db will equal secant squared theta d theta, and when um, b is 0, tan inverse of b, basically, because now we are finding a theta, so tan inverse of b is also going to be 0, so theta is also 0, and when b is 1, theta is tan inverse of 1, which is pi by 4 exactly. So we have exactly what we need for our substitution. So I is nothing but pi over 2 times the integral from 0 to pi over 4. What was db? Secant squared theta d theta divided by, well, let me actually show you the steps. Square root of b squared, which is tan squared theta plus 1, and by the identity that I showed you a couple of minutes ago, you can simplify the denominator into secant squared theta, and the square root of that is just secant of theta. We can cut out one of the secants. We have pi over 2 times the integral from 0 to pi over 4 of just the secant of theta d theta, and now we have another formula for the integral of secant of theta, that's namely, well, pi over 2 as it is, the natural log of absolute value, because we can't have a negative inside a natural log, secant of theta plus tangent of theta, but evaluated from pi over 4 to 0. So when I plug in, say, pi over 4, secant is nothing but 1 over cosine theta. This is nothing but sine theta over cosine theta. I'm just writing it because it will be better to evaluate stuff later on. So pi over 2, and then when I plug in the upper bound, I have cosine of pi over 4 is 1 over square root of 2. So 1 over 1 over square root of 2 is just square root of 2, and tan of pi by 4 is just 1, minus pi over 2 times the natural log of, when I plug in 0, cosine of 0 is 1, 1 over 1 is 1, and sine of 0 is 0, cosine of 0 is 1, so 0 over 1 is just 0. So we finally have pi over 2 times the natural log. Well, this is always going to be positive, so we don't need our absolute value sign anymore. This is just the natural log of 1. Natural log of 1 is 0. So that goes away. And we end up with pi over 2 times the natural log of square root of 2 plus 1. Now, I don't know, just for fun, we can try multiplying and dividing by the conjugate of square root of 2 plus 1 in the numerator and the denominator, just to obtain another answer expression. So we have pi over 2 times natural log of square root of 2 squared is 2 minus 1, using the difference of squares identity. So 2 minus 1 is 1 over square root of 2 minus 1. And now by the virtue of log properties, I can pull out a negative and then flip the argument inside to obtain square root of 2 minus 1. So yeah, I mean, we obtained two expressions for our original problem I. So to conclude, we have I, which was defined as the integral from 0 to pi over 2 of the inverse tangent of sine of x divided by sine of x dx. We used Leibniz rule or Feynman's integration technique to obtain pi over 2 times the natural log square root of 2 plus 1, otherwise known as negative pi over 2 times the natural log of square root of 2 minus 1. So that's a really neat result we got there. So that's it for this video, guys. I'm sorry if I didn't skip steps. If this video is long, or yeah, if you like kind of bored, those of you who are experienced with this technique who got bored in this video, I apologize, but I had to start somewhere from scratch, right? For the people who are learning about this technique the first time. So that's it for this video. Please like, share and subscribe. Recommend me to your friends. If you have any doubts, reach me in the comment section. Peace out.